All right, so this is problem 2.135 on page 82. Find the magnitude and direction of the resultant of the two forces shown, knowing that P is 600 newtons, Q is 450 newtons. Let me sketch it at the board so we can think about it the right way, hopefully. So we have a three-dimensional coordinate system, and it is a right-handed coordinate system. What do I mean by a right-handed coordinate system? Well, if you take your right hand, you point your fingers in the direction of x, turn those fingers along the shortest angle to get to y, then your thumb will point in the direction of the other axis, z. You see? So x into y equals z. It's actually cross products. We'll learn about that next chapter. But anyway, that's why it's a right-handed coordinate system. Of course, they're all right angles, but that's not why it's a right-handed coordinate system. Okay? You can have a right or orthogonal, in other words, where everything's mutually perpendicular coordinate system with z pointing the other direction, but then it would be a left-handed coordinate system. Because then x into y would be z into the coordinate, you see. Anyway, so there's the setup. Let me draw a couple of lines here for reference. So back in the xz plane, going back behind the x-axis, there's a reference line at 30 degrees. And then from the z-axis coming towards x, there's another reference line at 25 degrees. Okay, now these lines indicate projections of two vectors where vector P begins at origin O and comes out something like this. And it's equal to 600 newtons. I should have drawn that at a little bit steeper angle, I guess, because there is a 40-degree angle off the y-axis. And then, of course, this, I haven't drawn this real well. Let's project straight down until that 25-degree line. Move z a little bit so it makes more sense. There we go. And then the other force Q is 450 newtons, and it's something like that, and measures 55 degrees off this line. So there's Q at 450 newtons. What was the question? Find the magnitude and direction of the resultant of the two forces. What does a resultant mean?
If the two forces were added together.
Yeah, just add them together. What do you get when you add those two together? Well, this looks like spherical coordinates to me because we've got an angle in the horizontal plane and an angle up. Whereas this one looks like, well, almost like coordinate angles because it's measured off of the y-axis. Okay. Now, why would I care about that? Well, let's decompose P into its components. Remember we played with SolidWorks last time? We were decomposing it. Well, how would we do that? Well, what I recommend you do is always go to the summary if you don't remember the equations and see what you got. It's just cosine relationships. Let's see if they've got it in the summary. They don't, so that's okay. We'll just dig into the chapter and find what we need. Maybe they've got, here we go. It is in one of the other summaries at the other section. Section, or page 63, has what we need. Now, why is it that I had to go back a couple of sections? Well, it's because I was looking at the review problems at the end of the chapter. The problems at the very end of the chapter can draw from anywhere in the chapter. Okay, you can always, though, use information, if I give it to you, that suggests where you will find what you need. In other words, if you look at a section, like, for example, section 2.4, well, there are problems immediately following 2.4. In fact, look in your books. 2.4 begins on page 54. Problems 71 through 98 go with that section. So where will you find the equations you need to solve all those homework problems? Easy. Pages 62 and 63. It's sandwiched right between the learning section and the problems. Okay. Anyway, so what we need are the so-called direction cosines. So the equations go like this. The cosine of theta x equals the component of the vector divided by the magnitude of the vector, so on and so forth for the other axes. Okay, so for the y-axis and for the z-axis.
I have a quick question.
Sure, go ahead.
And it's like a simple question. How do you find magnitude?
Magnitude, there it is, 600 and 450, they gave us the magnitudes.
Wasn't the question for the problem, find direction and magnitude of P and Q?
That's what we're working on. The way we're going to do it is get the components of each vector, add them together, and then find the magnitude of that resultant vector. Does that make sense? So we're not there yet, we can't do it. Basically, let me answer your question. You're saying, let's approach this from the other end. Let's not start from the point where we're taking all the things that are given and just magically know what to do and put it together to come to an answer. Let's approach it from the answer and work our way back. We can do that. So there's going to be some resultant. This resultant will simply be Q plus P1. That's what a resultant means. So how are we going to find the magnitude of this resultant? Well, this resultant is going to be represented, let me do it this way, as Rx in the I direction plus Ry in the J direction plus Rz in the K direction, right? So if I want the magnitude of that vector, all I will have to do is take the components of the vector and use Pythagorean's theorem in 3 dimensions, like that. Does that answer your question a little better? So your first question is probably, why are you bothering adding these two vectors together? Well, because I need the resultant. Why do I need the resultant? So I can answer the question and give them the magnitudes. Okay?
What does the line over the letter mean again?
Means it's a vector, so it has magnitude and direction. Good question. The line above just means it has magnitude and direction. In your book, they use a bold-faced letter to indicate vectors. Okay? Something that has both magnitude and direction. Good question. Anything else? Clear that's a Y. Sometimes I start a problem from what I would call the ground up, where I take the pieces, get the things I need, put them all together, and there we have the answer. Other times, I'll start from the end. If you're ever confused, it might be that I should start from the other end of the problem. Start from what's asked for and work my way backward. So you'll see why I'm doing what I'm doing. Now, Rx, Ry, Rz will simply be Qx plus Pxi plus Qy Pyj plus Qz Pz K. See that? So that's why I need all these components, and this is just a generic equation, right? I know there's no vector in this problem called f. That's okay. This is just generic. F is just a vector. It's kind of like x is a number in algebra, okay? So if I could find the magnitude of q, well, guess what? I already know it. Then I can put it in here. If I could find the direction, the angle off the axes, then I can put that in here, and I could solve for the components of q. Get them, put them in, solve for the components of p, get them, put them in, and away we go. You see? Does that make sense to everybody? Any questions? Okay. I'm going to black marker, see if it works any better. So basically, my general approach is, let's take these that were given, rearrange them, and say that fx, for example, will be equal to f cosine theta x, so on and so forth for y. Why bother writing? It's the same thing. Okay. Notice I've already got the magnitude of each of the two vectors. Now what about the angles? Well, what would this 40-degree angle be called in this terminology? Well, that's the angle off the y-axis, isn't it?
Mm-hmm.
Isn't that theta y?
Mm-hmm.
That's what it is. Is this theta z then?
Yeah.
Nope. Theta z is measured from the axis to the vector. This is measured to a projection of the vector. So it's not what we want. If we could get this angle, that would be theta z. But we don't have theta z. Okay? Do we have theta y for q?
Is it at 55 degrees?
It's not 55 degrees because 55 is measured off the projection. But remember that q and this projection are all in the same plane. And so what would this angle be?
35.
Right, because that's a right angle, so that would be 35 degrees. Because 35 plus 55 would give you 90. Right?
So that means that would be.
So we've got theta y, so to speak, for both q and p. So that's not so bad.
I mean, theta z would be 60.
Theta z,
50,
no.
50, I
No, I don't think so. I think you're measuring the angle of the projection. We don't know the angle in, for example, this plane. Think of a plane that's at an angle. Remember, Q points back. It's got a component in the negative z direction. It's not in the xy plane. And so this angle is not just coming from x in the xy plane. It's in a plane that's tilted back a little bit.
I was just thinking that we had that theta y and down to the z-axis.
Theta y,
No, other side.
from here to the z-axis,
No, right underneath where it says P equals 600 newtons, you got that 40 degrees,
right?
right? Isn't that,
Well, that would not be down to the z-axis. This is above this projection line. So when you say this angle is 50 degrees, I agree with you, but that's not the angle to the z-axis. Because the angle to the z-axis is in a plane tilted back, right? Because P comes forward. P is not in the YZ plane. It has some x component.
I got that now.
Go ahead.
So, theta y has two components, one for P and one for Q.
Sure, there's a different theta y for P versus Q.
So which one do you put into the equation?
Well, it depends on what you want. If I want Px, I will put P cosine of theta y, well, if this is the y direction, for P, right? Good question.
So when we get PY for both, would we add those and that's how we get the resultant Y?
That will give us this piece of it. Yeah.
But will that give us what we're putting in?
Yeah, this
For RY.
PY will go in right there,
Oh,
just like QY. Now, obviously, this is a different,
oh yeah, it'll go in right there, and then the combination of those two will go in
yeah,
RY.
we'll add these two together right up there.
Okay.
Yep.
Is theta x 85 degrees?
Nope. You will not be able to calculate theta x trivially from what we've got. Because remember, these vectors have all three components. So while I'm drawing on a two-dimensional board, remember that Q is not in the xy plane, P is not in the zy plane.
Okay.
Remember how I drew that last time in SOLIDWORKS? We had other planes that were at angles.
I can kind of see how it's like three-dimensional.
Right. So getting this angle here is not trivial. Okay? It's not a matter of taking 90 degrees minus 40 because there's not a 90-degree angle. In fact, this line, and this line are not in the same plane. Okay? It's a good question, though. Anything else? Anything else? You guys are asking good questions. Okay. Well, let's continue then. So how are we going to do this? Well, generally the way you solve a problem like this is you go ahead and you calculate the magnitude of the projected vector itself. So could I calculate the magnitude of the projections? Sure. That I can do. Sorry, that came off. I meant to have that come down a little bit farther and replace the black line. That I can do. Why? Because notice that the blue lines and red lines are all in a single plane. Okay? So I do know the angle here, for example, if I want it. Or I could simply say, well, the length, we've already calculated the length of this side, right? Well, we were able to. What is the length of this blue side? What would you call that? Or the length of this blue side. Can you see it? Isn't this simply PY? Yep. And that's QY, isn't it?
Okay.
Right? So I could calculate the length of this side if I wanted to. That's no big deal. Because notice I'm just playing with a right triangle here, right? So what would the length of this line be? How would I calculate that?
Well, you
Wouldn't
have
it
the
be-
55 degrees, so you can use the cosine of
Yeah.
that times magnitude, which is the magnitude of 450.
So let's call this QXZ. Your book uses QH, for example, instead in the horizontal plane. I would rather use QXZ. In other words, the length of the vector that's in the XZ plane. Okay? That would be equal to, just like you said, the cosine of 55 degrees multiplied by the magnitude of Q itself. Okay? By the way, one thing I commonly do is I abbreviate cosine as C, so I write this Q cos 55 degrees like that. Okay? Now wait a second. You've been playing with right triangles for quite a while now, right? You know that you usually use sine and then you use cosine, or vice versa. Use the two. How is it that I'm getting a vertical component here and what is essentially a horizontal component by using only cosines? What's going on? Notice that to calculate theta y, you know for q, let me ask you, what is theta y for q? Can you give me a number?
35.
It's 35, isn't it?
It's because you're using the rest of the 90 degrees.
Exactly. And
Yeah,
that's
it's on the
rest of it.
right side, it's towards Q, and the 40 is for P.
So had I used 35 degrees here, I'd have to use sine. You see? I don't remember which was given. They either gave us the 35 or the 55, whatever. I'm just looking at it geometrically, okay? All right, so that will give me Q in the XZ plane, which I can then take and break into components along the x-axis and the y-axis, you see? So basically the x component plus the z component, I think I said that wrong. I meant the z-x axes. So the distance along the x-axis plus the distance along the z-axis, which is in the negative z direction, plus the distance along the y-axis gives us an equivalent to the vector q. Okay? Questions so far?
Is it at this point where we set up our q of x, q of y, q of z to start
I
solving
think
it?
so. I think we could start solving it, but let me set up the rest of the equations, at least for q.
Okay.
So qx would be equal to qxz times what? If I want this x component, I've got a 30-degree angle. Let me move that. Well, let's just reiterate it. So you can see that 30-degree angle. If I want the x distance, and I've got a 30-degree angle, notice I'm just playing with a right triangle in the horizontal plane. What would I use? Multiply by what?
And you're trying to get the X,
Yes, this piece.
then wouldn't that be cosine?
Good. Cosine 30 degrees. Everybody see that? How about to get QZ? QXZ times what? Sine 30. Exactly.
Wait, can you explain them? Like, cause for Z, when you say QZ, it makes me think that you're trying to get, like, the Z.
This thing here is QXZ. This thing, that
Oh,
projection.
why
That's QXZ because it's in the XZ plane.
It's in an XZ plane.
Yeah.
Is it like, okay, could you explain why or how it's in an XZ plane?
Because it's the projection of Q onto the XZ plane.
Okay.
Do you have the book
But
with you?
Uh,
Do you have a device where you can open up the PDFs that I give you? Did I give you the second chapter?
I
or-
left it at home, but, yeah.
You
don't
gave
know if
us
I
up
can-
to the 3rd chapter.
Oh, that's what I thought. Look on someone that has a book. So look at the problem, because seeing it on the, the better printing, the better drawing of it in the book will help a lot. So see if you can rectify what you're seeing there with what I've drawn up here.
So, well, when I see XZ right there, like, I just think it's in like, not that I think it's in the XY plane, but it doesn't look like it's in the Z.
You have to stop thinking about X and Y and Z being somewhere that you're used to them being,
Okay.
and understand what's actually given. So X is given to the right, Y is given up, and Z is out of the board toward us.
Okay,
Okay? So where is the XY plane?
just,
The whole board.
yeah,
Where's the YZ plane? Coming out at us.
yeah, and then,
How about the XZ plane?
I guess,
Coming out at us but horizontal, right?
okay, yeah.
So
Okay.
up there is actually the X negative Z plane,
Do what now?
the other side of
You
it.
could,
The other side going into the board.
Yes.
Yes.
Yeah, that'd be the negative Z direction. Yeah.
you could see like YX as being that wall,
Mhm.
ZX
Right.
as being the floor, and YZ as being that wall, right?
That's right. Yep, you got it. So the important thing to realize is that Q is not just pointing back into the board, it's pointing up to the right and into the board. So it's going out of this, if you put the origin, like you said, at the front corner, front left corner of the classroom, then Q is pointing out, basically towards the men's bathroom, right? But up to the right of it. whereas P is pointing sort of back towards that corner, right? Half of this is visualization. You gotta be able to see what all these things are and where they are. And that can be difficult at first. Does it make sense now where QXZ is?
It's like, I guess like pointing like right there, right?
It is, right. It's kind of across the floor going that way.
Oh, it's gonna be
Well,
like that. way.
right. Well, actually from that corner going that way. But it would stay on the floor if we put the origin of that upper lower cone.
Yeah, that doesn't really make sense how that's part of Z. I mean,
Well, Z is coming out positive this way, but Q has a negative Z component.
oh, it has a negative Z component?
Right. Yeah, if you look at the picture.
Figure 2.135, right?
Yes.
It's not 0.135. I mean, I can see what you mean by negative Z.
Okay.
Yeah, negative Z does.
So what if that 30-degree angle were 0? What would that do to Q?
Make it just, it would lower it.
It wouldn't lower it. Where would Q be? It would still be 55 degrees off horizontal,
Fall along this wall, right?
all along this front wall. You see, that would put it into the XY plane, right? So it would be sitting in the XY plane. All that 30-degree angle does is move it out of the wall with
Oh.
a negative Z component. Does that make
Okay,
sense?
so that's 30 degrees from the X plane?
That's from the X-axis in the XZ plane. Yep.
Yeah.
Does that make more sense?
Yeah.
Okay. Good question. If you're confused, so are others, so this is a good question. So now, if we take, well, I think we can just plug and show, can't we? So if we get, I'll tell you what, you do it, grab your calculators. You know the magnitude of Q, it's 450 newtons. You can take the cosine of 55 degrees. So tell me the magnitude of QXZ, and I'll put it in blue, I guess.
258.109 newtons.
258.109,
Yes.
thank you. Okay. There's some human factors colors here, so Q times cosine of 45 degrees. And then if we want to get the X and Z components, let me get rid of these, because I guess we don't really need these right now. What I really wanted was this, but we can copy that format down to the other axes. We'll take care of that in a second. So if I want to get QX, can you see that QX is right here? And this is then what? What is that?
Oh, I can see what you're pointing to.
This line going back into the board? Anyone can answer it.
It's about like the angle line, like the 30.
This angled line is not 30 degrees. The 30 degrees is there.
Yeah.
This line is going back into the, straight back into the board.
X, Q, X, Z.
No, QXZ is right here.
Yeah.
This line is not QXZ. This line has no Z or no X component.
Okay,
I can see that.
that is the one we have before, the XZ with the cosine of.
Well, this is Z, isn't it? Just QZ? That's the length of Q along the Z axis.
Okay.
Okay.
Does that make sense?
I think
So that's this.
I think the red marker is just going out.
Yeah, I agree. It's probably not writing very well. Let me try a green instead. There. Is that better?
Didn't see that.
Yeah.
Yeah. So we still have that right angle there in the XZ plane. I've obliterated my X now. That doesn't sound right. I've obliterated the X label on the axis. How's that?
And the X.
All right, so if we have QXZ, which is 258.109, could we then calculate QX and QZ? I think we could. So let's do that. I'll try to write one more thing in red, just the magnitude of QX, the magnitude of Q along the x-axis. But I need your help. Take QXZ, multiply it by cosine of 30, please, and see what we get.
223.529. You need more?
That's enough. Probably more than we need, but that's fine. Anybody have QZ?
It's a race.
129.0546. That'll work.
Did I round it properly?
Uh,
What you said? But you said
Yeah.
4.6 at the end. So now we have all the Q components. We've got these bits. And by the way, getting PY is going to be very simple. Why? Because we've got the coordinate angle off the y-axis. If we just had the coordinate angles to the vectors, not the projection, but to the vectors, we just use cosines everywhere. That'd be easy. But we don't. We had to get the magnitude of QXZ. What do you think I'm going to try and get next?
P.
Q1.
Stuff with P.
We could get PY. That's the easy one. Let's go ahead and take care of PY so we can stop thinking about that, and then we'll go from there. You're right. PY is the easy part. That's this vertical part here. So that would be 600 newtons times what? Cosine of what?
Right, so it's
40 degrees.
40 degrees.
Real quick,
Sure.
would you mind explaining again how, you said if it was this way, we'd be able to find everything using cosine. Would you be able to repeat that?
Yeah, sure. If we had the coordinate angles, in other words, the angles to the vectors from each of the axes, we'd be able to use an equation like this, using the angle from the coordinate axes to get all the components of the vector.
We have
We don't
some-
have that. We
We have
only have
some
one.
of them,
We
right?
only have one for each.
One for each, okay, but.
We don't have it for the angles coming off the x-axis or the z-axis.
But we have them for the projection?
We have, well, we have
For
the,
two projections?
right, we have those angles from those axes from the projections, that's true. But that's not good enough for us to just use this.
Okay.
For that last one, it says QZ equals QX, yeah, what's that?
QXZ?
QXZ.
times sine 30.
Yes, times sine 30. That's what it says. But we're over here calculating PY. That's this magnitude, this vertical magnitude of P. Does anyone have that number?
Uh, 459.6.
0.63.
So now we have QY, PY, QX, QZ. Now what do you think I should do next?
Add them.
Well, we don't have everything we need. We still need
Oh, so
PX
we need
and PZ.
PX.
What are we gonna have to do to get PX and PZ?
To get PX, you need P,
We need to find the angle off of
the
that
P
projection.
and
like,
X.
Okay, so there's 25
We
degrees.
find the magnitude of that.
Oh, you want the magnitude of this projection? Good. What would you call this projection based on what I've called the other?
It would be ZX.
Yeah, PXZ, PZX, whatever. Yep. So I would call this projection PXZ because that's the projection of P in the XZ plane again.
So why, so you're doing it off the projection, so why wouldn't you like do it based off the x-axis?
Because I don't know the angle off the x-axis. I don't know the angle of vector P off the x-axis, so I can't. I can't go directly for something like this because I don't have the angle. I can't go with this 25-degree angle because the 25-degree angle does not go to the z-axis or between the z-axis and the P vector. That's the angle to the projection of the vector. It's a different thing.
Yeah.
Good questions. I like all this discussion. So how am I going to calculate the magnitude of PXZ? Any idea?
600, wait, PXE, 600
P times
sine 40.
sine of 40 degrees.
Wait,
Anybody agree or disagree with
I
that?
disagree.
Yeah, what do you think it is?
Wouldn't it be, if we're trying to find PXZ,
Yeah, which is
Or-
the projection, right?
Okay.
we're gonna use the other, aren't we using the
The,
angle to the projection from P?
It'd be cosine of 25, right?
No, because 25 isn't
25 's
to
in
P.
this-
Well, if you
Right.
want cosine, you could do 50 degrees, couldn't you?
Well, I was gonna say
It's a
50.
good discussion.
I was gonna say 50 just generally, because I thought it was going from.
So do you wanna take sine or cosine of 50?
I thought it was sine. Wait, hold up, let me look at it. 50, magnitude there, and we want that, so, we want cosine.
Okay. So we could look at this line right here. It's the same line, right? We already know that line's magnitude and a required cosine because that's the angle touching. Do you see the right triangle there? So the reason that it's sine of 40 is because this is the side that is opposite the 40-degree angle.
Okay.
Or you could take cosine of 50, which is exactly the same number.
Okay.
Okay, so if you insist on using cosine, fine. Just use this angle, and now you're looking at this right triangle. See that? All I did was draw a big rectangle. That's it. Okay. So, let's calculate its magnitude. Any questions on this? I still see confused looks. It's okay if you have questions. Go ahead.
Could we also use the, like Pythagorean theorem to kind of solve it if we have the,
Sure, you're saying we've got P, we've got PY, it's a right triangle, use Pythagorean's theorem, get PX. That would work also, yes. Good. Good question. Anything else? Okay. So, 600 newtons times the sine of 40 degrees gives us how much projection in the XZ plane?
385.67.
Those are newtons, thank you. So now how am I going to get the components PX and PZ? How do I do that?
Make a right triangle between PXZ and the Z axis.
So you're saying, we've got a right triangle in here, don't we? Right? And what is this?
That would be sine of 25.
Now, what would we call this length?
PX?
PX. Notice that it's parallel to the x-axis. See that?
Yeah.
What would this length be?
That would be.
PZ.
That's right. Do you see the right triangle now? With PXZ being the hypotenuse?
Yeah.
Okay, so help me calculate. You tell me what to write in order to get PX. Don't tell me numbers. Tell me symbols.
P.
PXZ.
Times.
Which one are we trying to get, PZ or PX?
PX.
Then we're gonna need, sine of 25?
Some people said cosine, some people said sine. How many people vote for sine? How many people vote for cosine? Retract your vote, cosine. Sine of 25 degrees. Notice that the 25-degree angle is over here, and this is the side opposite the angle. Okay?
Why is it times PXZ?
Because PXZ is the hypotenuse of the triangle we're playing with. Good question. What else? All right. So, what about PZ? Tell me an equation there also.
It would be PXZ
Good.
times the cosine of 25?
That's right. Just the other side of the triangle, right? Because that side is touching the angle. So now let's fill in some numbers and see what we've got. So what is this? 385.67 newtons multiplied by, which are we doing? Z, so sine 25 degrees, I mean X, not Z. And the other equation, 385.67 newtons times cosine, 25 degrees. Okay. Once you have a number for these two, tell me what they are. I'll fill them in at the board. Tell me whether you're giving me PX or PZ. In fact, I'll tell you what, this side, give me PX, this side, give me PZ. Okay?
PZ is 349.5 3, 8, 0. You need more?
Take 4 and be done with it. Other side of the room, PX.
PX is 162.992.
Thank you. So now we have everything that goes into the equation, right? We've got PX, PY, PZ, QX, QY, QZ. And so now we can calculate the magnitude of the resultants. Let's see, let me make a note. This is PY. There we go. And then, let's go from here and figure out what the vector R looks like. So we need QX plus PX. So we got it all at the board? There's PX, here's QX. So add those two together for me if you would please. 223.529 plus 385.97. I guess I got lazy and stopped.
609.5.
609.5. And that's in the I direction. Okay. Seem reasonable. It's PX, so yeah, that seems reasonable. Good.
Okay.
How about the Y components? So PY here plus, I shouldn't have put a box around that. I'm trying to differentiate it. Let me do it differentiate. QY plus QY. Where did QY get off to? Did we ever calculate? Yeah, we must have calculated it at some point. I bet I've erased it. How would we calculate QY?
Would that be, would be the cosine?
Of which angle?
Cosine of 55.
No, not 55.
Q sine 55.
Sine of 55 or cosine 35.
Oh yeah, because you're trying to find, that's right, that's right.
Right? It's not because it's vertical, it's because if you use a 55-degree angle, the 55-degree angle is opposite. The 35-degree angle
It's
cuts.
because it shines on QY.
You got it. That's the way I think about it. So I've erased it. Somebody calculate it for us. If
So
you-
wouldn't it be sine of 55 times 450?
Yes, sine of 55 times 450. That's it. So what's that number?
It's 368.62.
I think we had that at one point. Maybe I've erased it, or maybe I'm blind and it's sitting right here staring me in the face. Anyway, so we've got QY, 368.62. Let's add that to PY. And that's what will go in for the Y component, or the J component of the vector.
Would be 828.25.
Since we're rounding to a single decimal place, I'll just take 0.3. Good. Now you tell me, how about the last component? What will we add together, and what's the result?
So it'd be 129.1 per QZ
Okay,
plus 349. So I'll just add that.
0.5.
Yeah.
All right, so PZ plus QZ, right?
So it's 478.6.
Anyone disagree with any of these numbers? All right, I'm going to assume these numbers are correct. They seem reasonable to me. Now, how are we going to get the magnitude of the vector? This is the resultant. If we were to plot this vector, notice that it all has positive components. What does that tell you about how big each of these vectors were? It tells you P was bigger than Q because P won, right? As a matter of fact, Q had a negative Z component but a positive X and Y component, whereas P had positive X, Y, and Z components. Not surprising that we end up with a fairly large X and Y component. This one's a little smaller because one took away from the other, at least it should have. But we added them together, we made a mistake, didn't we? Because look, the Z component of Q was negative, and we just took QZ 129 and we added it to PZ, what should we have done instead?
Subtracted it.
We should have subtracted because it's going off in the negative Z direction. So we should have taken PZ 349.54 and subtracted 129.06. Let's do that and let's correct our Z component. It's okay. How many people saw that and thought, wait a second, that doesn't make sense? Anybody? It's okay. It's all right. You're getting there. So to be clear, I should have said this is a negative thing. So how much is it, 220 you said?
Mm-hmm. 0.4.
That's better. So if we were to sketch R, it would still be, you know, in this direction, but it would have a smaller Z component than it has X and Y components. Another way to do this is to take Q and put it head to tail with P. That's essentially what we've done here. Okay? But graphically in SolidWorks, if we were to draw this in SolidWorks, we could just draw a line coming off of P parallel to Q, make it the length of Q, and from the origin to the tip of Q would be R. Maybe we'll shut off the camera and try that with SolidWorks. There's no point in pointing the camera towards that screen. Okay? And we'll see if we get the same thing. But let's finish off the problem. They wanted to know the resultant magnitude, I believe. So what are you going to do to get the resultant magnitude of this vector? Just what's above, right? This is Rx. And this is Ry, and that is Rz. Okay? So, the magnitude of the resultant then is equal to what?
All of those combined.
Right, so combine them. So 609.5 squared plus 828.3 squared plus 220.4 squared square root is how much?
$1658.2.
So basically 450 newtons plus 600 newtons is not 1050 newtons, is it? And something's wrong because our resultant vector should not be bigger than the sum of those two. Because if you just add 600 plus 450 along a straight line, that's the most you can get out of it. So something's wrong with our calculations somewhere because...
Look at the X.
Look at the X. You think the X is wrong? Let's see. Unfortunately, I've erased PX. They're both positive. We should be able to calculate PX. We still have this.
169.22.
169.22?
162.99.
Yes, 162.99 is what I have as well.
Okay. So if we add PX with QX, we shouldn't get 609.5. We should get less. I don't know what went wrong, but yeah, you're right, this number is not correct. So 162.99 plus 223.53 is how much? It's about 163. Well, isn't that just 386.5? I'm thinking right? Yeah, 386.5. So now let's try again. Let's take the square root of the sum of the squares with these and see what we get. How did I figure out that was wrong?
Because the total was bigger than P and Q total.
Right. And they're in different directions.
Yeah.
So just like before, when I told you that 3 plus 4 equals 5, I convinced you because I drew a right triangle, right? That when you have direction included in your consideration, then things work a little bit differently than just adding along a straight number line, right?
940.23.
That sounds practical and reasonable. 940.3, you say?
Point 23.
Point 23, okay. Yeah, we've dropped the second decimal place a long time ago, so let's just leave it there. Okay. Any questions about this? It's easy to make a mistake in these problems. I don't actually care very much about your final answer, especially on exams. I care about your method, okay? Which question?
I just wanna make sure my, like, brain is wrapping
Sure,
around this right.
sure.
But, so what we did is we found out how much force there is in each direction from each component, and then
Yes.
we found out how much force there is in each direction from both components, and then we found out the total.
That's correct. You got it. Yep. We broke down the two vectors into their components, x, y, and z, by hook or by crook, whatever we had to do, since we didn't have all the coordinate angles. And then we added those components together, the x components from both, and that was our resultant vector, you know, x, y, z. And then
How do we find the direction from here?
How do we find the direction? Ah, that's a good question. Notice that we've got the x, y, and z components. So we basically have 2 points on the vector. Now, I'm going to do something, because this is getting really messy. I'm going to erase everything except for the coordinate system, okay? And I hope we got the numbers right. We'll see in a second. We'll solve it in SOLIDWORKS and find out if we did it right or not. I'm going to attempt to draw that vector to scale. So let's see, let's tick off hundreds of newtons here, okay? So there's 400, etc. But make the scale about the same over here. What do we have in the z direction? 220, so that's more than enough. There's 200. And in the y direction, I need to get up to 800. So let's see, 100, 200, 300, 400, 500, 600, 700, 800. Now what I'm going to do is go to a z value of, it doesn't really matter where you start. Z value of 220 is, right about there. Okay, so this line, and really a plane parallel to the xy plane through this line, is what's defined by that 220.4, right? Newton dimension, okay? So right there is 220.4 newtons. I'm trying to make this line parallel to the x-axis, but I'm failing miserably. There we are. So then in the x direction, we're at 386.5. So let's see, there's 400, there's 350, 386, right about there. So this line, parallel to the z-axis, is the line that contains x equals 386.5. Okay. So do you see how vector r must project into the xz plane like that? Now the last component is the 828 Newton component. So I've got to go up on an axis parallel to this one, 800, let's see, how can I do it? Right about there. Looks good. So that should be 828, well, maybe a little more, 828 newtons on the y-axis. And this is a point directly above the projection. So vector r is right there. Okay? That is vector r. That's the sum of the two vectors. But your question is, how do I find the angles? Well, my question to you is, which angles would you like? Let's find all of them. That's a trick question. All right? When SISC asks you which one do you want, we're going to get all of them. Okay? Why? Because we can. So let's start off getting this angle, because that's an angle that was given. It's a coordinate angle. It's off the y-axis. P and Q is given, right? So let's, or pretty close to it. So let's get this angle, which is, of course, theta y for r. Okay? How will we get that angle? Well, we'll have to set up a right triangle. What right triangle do you see? This one. See that right triangle? Here's the right angle, right there. So that means we're going to need the length of this side. What is the length of that side? That's the length of the projection. So we're going to have to take 386.5 squared plus 220.4 squared square root. So go ahead and do that. And this is what I will call RXZ. So square root of the sum of the squares of RZ plus RX. And you have RZ and RX, don't you? So give me that number if you would, please. So RXZ is down here, it's also up there. We're just interested in length. Maybe 500 something, isn't it?
444.93.
Oh, yeah, I'm not thinking right. Okay.
444.93. 220 squared plus 386 squared, right? Or like, you know,
Yeah.
the
Yeah.
decimals added on.
Yeah.
444.93.
Okay. So now that we've got the length of this side, bless you, do we have the length of this side, R?
I mean, yeah, because
We
that's
have.
our final answer.
So to get theta y, what's the relationship between RXZ and R? Along with this angle theta y.
It's, well, the R.
R is the hypotenuse.
Yeah, it's the hypotenuse.
So are we talking sine or cosine here?
Oh, we're talking, to get the.
This is
angle.
gonna
Theta
be
y.
opposite, so it's gonna be arc sine of that over that, right?
Sure, but it's a sine relationship.
Yeah.
All I'm saying is
Yeah.
that RXZ over R is sine theta y.
So you know how you can explain how, if you already have the angle and you're trying to find a side, how if it shines on the side, it's sine?
Right.
Could you explain it like that in how you know that it's sine, you find theta y?
Theta y shining on RXZ.
Okay. Okay, cause we have two sides, like the R, like the resultant R and RXZ.
You're saying there's another angle we could be interested in? Is that what you're saying?
Uh,
You're saying we might be interested in this angle, which is also that angle?
I like your explanation.
Okay, you're good with what we had?
Yeah.
All right. Good questions, anything?
Okay, but what if the angle that you're trying to find wasn't where it is now?
What if it was in the other corner?
Yeah, what if it was there?
Well, then it's touching the side we're interested in.
Okay. Oh, then it's cosine.
That's cosine.
Well, it's touching both sides that we're interested in.
No, it's not.
Are we interested in both?
This
of
is a
them?
side, that's not a side, this is a hypotenuse.
Okay,
That angle does not touch both sides, it touches a hypotenuse and a side.
okay. I thought the hypotenuse was one of the things we were interested
R is the hypotenuse.
in. Yeah,
And it is one thing we're interested in, but something we have.
okay.
Good questions, what else? You know where all this vector stuff is particularly useful? Video games. If you like video games, they're usually a whole bunch of vectors, a whole bunch of polygons, really. Used to be you couldn't do as much math as you needed to run a polygon-based game, but then the 90s came along and better processors, and just kept getting better from there. Anyway, so why does SolidWorks still run so crappy on modern hardware? That's a great question.
A question we will never know the answer
Good
to.
question.
Oh, I know the answer to it.
That's a good question.
All right, so theta y. Somebody tell me theta y. You've got the equation. You're right. It'll be arc sine or inverse sine of RXZ over R.
What did we say the resultant R was again?
940.2.
So, you do, point 0.47 times, well, that's what RXZ over resultant R
Where is
is. Oh.
So take the inverse sine of that number.
The inverse sine of the number,
Was that 28 point?
that's right. Yep.
Sounds reasonable.
Yep.
28 point what?
2,
2?
4.
That's good enough. Now, similar angles to what they gave us would be something like, I don't know, that angle, or the other one off the z-axis to the projection. How could we find this angle?
That is the inverse sine of,
I like where you're going, let's see if you got it.
RXZ.
Okay, top or bottom, RXZ?
It should be, on the, it'd be on the top.
No, it's on the bottom. I like where you're going, keep trying.
And, under Y, like the projection of Y? Or no,
Well,
no,
RXZ
over
is a
X,
projection.
Over RX.
Not RX, RZ. Why? Notice that RZ is this side, isn't it?
Yeah.
Which is this side, and so that angle shines on that side, so to speak. So it's a sine relationship between this side and the hypotenuse. But this length is RZ. If you use RX, you'd have to have inverse cosine.
Okay.
Okay? So let's just call this angle, I don't know, I don't want to use alpha, beta, gamma, or theta. I don't know, lambda. Let's call it lambda. No, lambda they use in the book for something else. What are the Greek letters of it? Phi? That'll work. We'll just call it phi. Thank you. So somebody tell me the value of phi. So RZ 220.4 over 9, no, not over 940, over 444.9 inverse sine comes out to what angle? And I'll leave these on the board because we're going to measure them in SOLIDWORKS when we build that model as well. That'll be off camera, unfortunately. To be clear, what we're doing is inverse sine of RZ 220.4 divided by 444.9, which is RXZ. Hopefully your calculator is set to degrees and not radians. Our final answer.
29.7.
29.7 degrees. Now, let's do something else. I would like to find the angle from the resultant vector down to the x-axis. That I would call theta x for r. Okay? I'd also like to find the angle from the resultant vector down to the z-axis, and that's an angle I would call theta z. Let me show you the triangle that we're now playing with. I'll put it in green. Its hypotenuse is r. Let me leave the hypotenuse red, okay, because that's the resultant vector r. Let me show you the side lengths of this triangle in green. So this is for theta z. It would include r, z, and a line going from here to here. So unfortunately, it's going to look like a very flat triangle, but the right angle is way down here in this corner. Okay? Maybe it would be easier to see the triangle that contains theta x, because it looks like I've just drawn over the vector, though that was not my intention. Okay? The vector r is still here. It is not green. So for this one, I will need rx and a line going from here to here, and this is a right triangle. Do you see the right triangle, how it's tilted towards us a little bit? Okay. That triangle contains theta x. So I will need the length of at least the hypotenuse and one side in order to get theta x, but guess what? I've already got the length rx. So to get theta x, does theta x touch rx or not? Yes. So it's a cosine relationship. So the cosine of theta x equals r over rx, and guess what? That's that equation that's in your book. Remember that? Here, go look at it. Page 63. Theta x is just a coordinate angle. It comes off of one of the axes, the x-axis in particular, and goes to the vector r. Okay. So basically, theta x would be the inverse cosine of r over r. I've got that backwards, I apologize. It should be rx over r, I'm sorry. So rx is 386 and a half. R is 940.2. Somebody tell me the value of theta x, please.
$65.73.
Does that seem reasonable? That may be reasonable. 65.73? Okay, thank you. Well, let's just drop it to 7. 'Cause if our numbers here only had one decimal, I'd feel bad taking another one.
I've been using a lot of variables and that's
Yeah.
what I've been getting.
How about theta z? How would we calculate theta z? You can look at it just based on the pattern of what we've got, cosine theta x. Look on page 63, the equations are sitting there.
Same thing, but with the z component instead of the x component.
It's that simple. So if we take the inverse cosine of rz over r, we should get theta z. So let's do that next. Anyone have theta z for me?
$76.437, or wait, 76.4.
Thank you. Now, unless we've made some mistake along the way and one of our numbers are wrong, the rest of this should be just fine. We've used the right approach. Okay. Any questions before we turn the camera off and jump over in SOLIDWORKS?